as well. It takes a few seconds to spool up on that side. And I'm gonna go from the general text channel to today's text channel. Alright. So I'm ready to go. 2 minutes and a half, and I'm ready. Okay, one last message from the general text channel. Yeah, I think the largest lecture hall in UC Davis, at least used to be Chemistry 192, if I remember the room correctly. It is gigantic. They used to show movies in that lecture hall to make money. So various clubs and whatnot would show movies. I think usually on a Friday night, and it does resemble a theater feel. I mean, it's that big, the lecture hall. So it's kind of interesting. And then the computer lab, the general computer lab used to be under, I think it was Hutchison Hall. It's like in the basement. Yes, that seems to be the best place to put all the computers. um, anyway, yeah, it was in the basement, and I used to be a TA, for computer science classes. Oh, okay. Yeah, we had Sun workstations at the time. I'm pretty sure they're all PCs running Linux these days. Um, yep, that's when I found out, when people debug their programs, they just randomly introduce changes to the programs, hoping that one of those changes will work. That was, yep, that was the, yeah, well, CS students don't need the physical Sun, and besides, they had Sun microsystem workstations already, right? Yeah, so we got a lot of Suns, in the basement. Yeah, I'm sorry, I couldn't resist that one. All right. Exactly, Chris. I know exactly what you mean. Just like it burns. It burns. Yep. All right. Well, it is noontime, and I am going to get started. So we got a few things to do. Okay, here is my notes, and I'm gonna continue to type this one, as we go. So the first question is, do we want to go over the set homework assignment? So I'm just gonna wait until I get the responses from people. Oh, okay, all right, cool. Let's do that. All right, so let's go to the set theory assignment, which I think is this one. I'm gonna open it in a new tab, and I kind of have to turn off student view because otherwise, I'll just get a big fat 0 for that one because when I turned it in, I didn't actually answer anything. So there we go. All right, so let's go through these questions one by one. And I am going to use a preview, which is kind of what you see, but not exactly the same. All right. I have to be honest, if I were to take my own classes, I would probably get a B because, I am actually very careless when it comes to like, minor details and stuff like that. So I probably will not be getting an A in my own class. All right. So the set A uppercase A has elements lowercase ab. The set B, uppercase B, has the elements lowercase a, b, and c. Which one of the following is true? So these are easy, right? Because only one of them is going to be true, so you can basically do it by elimination. Well, fortunately, the first one is correct already. A is a subset of B. The second one is wrong. Not that it is not possible, it's just not right in this case. So in this case, the set of AB is not an element of the set ABC. B is not a subset of A because B has more elements than A does. And B certainly is not an element of A because there's nothing in A that looks like a set. So there we go. Alrighty. Yeah, we're going to go through all the questions. So by the time we get to question number 6, we'll address any specific questions about that. There we go. Okay, so question number 2, A union B is A, B, C, D, E, and then A, the difference between A and B is CE. Which of the following combinations of definitions of A and B would satisfy this constraint? Select every combination that meets the constraint. Okay, so let's go ahead and get started here. Alright, so let's take a look at the first line. Okay, so the first line, the union will work, and then the difference is not going to work. So we rule this one out. So if A minus B, or if the difference between A and B is CE, we know that C and E has to be in A, but not in B. So the second one also has CE in it, and B has ABD. So the second option actually would work. The third option would work as well because CE is already in A, and then B has the remaining items in order for the union to work. So the third one is going to work too. The fourth one is not going to work because in this case the difference is going to be A, B, C, D, E, all of them. And then for this one, it's also not going to work because in this case the difference is going to be the empty set because everything in A is also in B. This is also not going to work because A is an empty set, which means C and E are not found in A but not in B. And then for this one, we have ACE in A, so this is also going to work because we can see that C and E as elements are only found in A but not in B. But when you combine A and B, when you have a union of the two sets, then we have all of the elements that we need. And then we have this one as the last one, which is kind of like this one over here, except B also has C and E, which will make it not work because in order for the difference of A and B to only contain C and E, we know that B cannot have the elements C and E in it. So there's question number 2. Let's move on to question number 3. Choose the correct answer. A is an element of a set that has an element which is also a set of the element A, and the answer is false in this case. There we go. Now, if you guys have any questions at any time, just go ahead and just ask the questions in the text channel. Alright, so this one, ABC is a subset of itself. Yes. Indeed, every set is a subset of itself. So there we go. And then in question number 5, we have the union of ABC and AB being just ABC, and that is also true. At some point in time, I should probably head out to either Chegg or Quora or what's the other one? Reddit, to see if I can find some of my own questions over there. That ought to be kind of interesting. For question number 3, A is an element of a subset. Okay, let's go back to number 3. That is wrong because A, in order for this to be true, the set can only contain A but not a set of A. In other words, A as an element does not equal to the set containing A, and as a result, this is false. Alright, 5, 6, there we go. Okay, so now we're getting into the fun ones. These are the actual fun ones. What is the value of the following expression? So we really need to look at all the options first. True regardless of how A and B are defined, false regardless of how A and B are defined, or the third one, which is sometimes it's true and sometimes it is false. Alright, so let's check this out. Okay, if A if the difference between A and B is the empty set, that means there's nothing in A. Let me see. There's nothing in A that can. Okay. There's nothing in A that cannot be found in B. There we go. So there's nothing in A that cannot be found in B, and this one here is saying it is not the case that A is a proper subset of B. So now we have to okay, so the question is, how do we approach this kind of problem, right? So to approach this kind of problem, you have to remember what implication is. So in order for an implication to be true, we have either the left-hand side or the precedent being false, or they both have to be true. The left-hand side and the right-hand side both have to be true in order for the implication itself to be true. In order for an implication to be false, yeah, that's a lot more limiting, because in order for the implication to be false, we need the left-hand side to be true and then the right-hand side to be false. So now we can try to think of cases to make that happen, right? So how many ways can we make it so that the difference between A and B is an empty set? Well, there are only a few ways, right? Okay, so that's one. So if A is empty set and empty set, then no matter what is in B, this is guaranteed to be an empty set. The difference is guaranteed to be an empty set. But we already know that an empty set is a subset of B in this case, because B has something in it. So when you have this side being true and this side being, let's see, this is true, not true is false. So we already have a situation where the implication itself is false. So if I have at least one case where the implication is false, then we can rule out the first one. So then we only have to choose between these two. Empty set is not a proper subset of the empty set. Alright, so let's plug that in. So Nathan is trying to say, what if A and B are both the empty sets? So if A and B are both the empty sets, then this is true, right? A minus the difference between A and B is still the empty set. But on the other hand, on this side, we have true as well, because the empty set is a subset, proper subset of the empty set is actually false. Not false is true, so we have true and true. So Nathan has just created two cases where one would make this expression, the implication true, and the other one would make the implication false. So the answer is, it kind of depends on how you choose your A and B. There you go. Implication is only true if okay, so it depends on the implication. Well, if you can make this side false, then the implication is true already to begin with. So all you have to do is to find a case where A minus B is not an empty set. That will make the implication true already. And that's pretty easy to arrange. In fact, you can have A and B not related at all. That would still make this false. Alright, and Nathan is still typing, so I'm gonna wait a little bit. But I'm pretty sure so the question is trying to ask us whether the implication is true for all cases, true or false in some cases, or false in all cases. That is correct. That is correct. That's what the question is asking. Alright, question number 7. Oh, Nathan is still typing, so I'm gonna wait a little more. Okay, so I'm getting to question number 7, which is true. Okay, so so Nathan said he was confused and thought that we were just trying to answer whether it is true or false. Well, there are 3 options. One is saying it is true no matter what you choose to be your A and B. It is false no matter what you choose to be your set A and set B. And the third one is saying, well, we don't know whether it's true or not, because sometimes we can make it true and other times we can make it false. So that's kind of the deal. Okay, gotcha. Well, the assignment doesn't really carry a lot of weight. It will be very strange if somebody's actual letter grade is hanging in the balance because of a few questions in one of the homework assignments. So I wouldn't really worry too much about it. Well, let's work on number 8. So number 8 says, A is an element of B implies A is not a subset of B. All right, so once again, we want to find out, whether it is the first one, the second one, or the third one. So let's create some cases, right? The only time A is a set and it is an element of B is to put that set in B. And the second one is saying, if A is an element of B, then A cannot be a subset of B. And that is false, right? Because we have already demonstrated that it is possible to create a case like that. All right, so Nathan has typed an example. A is the empty set, B is a set of the empty set. So that would make A an element of B being true. So that means the left-hand side is true in this case. And then on the right hand side, A is a subset of B is true because the empty set is a subset of everything, including itself. And then the negation of true is false. So, excuse me. So now we have true implies false, which is false. On the other hand, it's easy to make A is an element of B being false, so that means the entire implication is true. So that means, once again, it depends on how we choose set A and B. Yeah, exactly. So Danny is correct. Generating examples would help. Luke has an example of A being X and being a set that has X in it, and X is just some set, right? So it's a generalization of what Nathan has typed. So that's a generalization, which is good, okay? Because once you generalize, then it's basically a pattern, like I was about to say regular expression, because it is just a pattern to describe many different individual cases. Okay, so Elijah said, he likes to break down the implication into disjunction. That's certainly, one way to look at the implication. You can define, implication as the negation of the left-hand side or the non-negative version of the right-hand side. So you can either memorize using the truth table, or you can look at it as not the left-hand side or the right-hand side. So either way works. It really kind of depends on your personal preferences. All right, so I'm submitting, and let's see, did I get all the points? Yep, I got 10 out of 10. Woohoo! Alrighty. All right, so you have a new assignment. So the new assignment is has to do with functions, and that one is due next Wednesday at noon, high noon. And I probably should say, Pacific. Let's see, are we? Yeah, we're still in Pacific Standard Time. We have not fallen back into daylight saving time, so it's high noon. All right. All right. What is that in Unix time? Actually, I have a tool that might help. I'm trying to think of the tool, the quickest way to do it. The quickest way to do it, interestingly, maybe using MySQL and then do a select. I think it's Unix underscore timestamp, and then now as a inside the parentheses. That's the one way I know how to do it. That may not be the quickest way to do it. Oh, Unix time. So Unix time. Oh, wait. Okay. Right. High noon. Yeah, so Unix time is basically time specified as not the number of seconds since 1970 January 1st, 12 a.m. And that's it. That's the number of seconds since that very specific moment in time. And Nathan has the time. All right, cool. February 21st is a holiday. That it might be. Let me check. Okay, I'm just gonna use this browser so you guys can all see. And American River College academic calendar. And we're gonna go check. Now, this is really annoying. Every single time it pops up. May I help you? No, you can help me by not popping up. Go away. All right. So we have spring, and yep, you guys are right. Okay, so George Washington birthday is February 21st. So that means I'm gonna have to move it. Okay, let's move that to Wednesday. Alright, so we are moving exam 1 to Wednesday the 23rd. There we go. It's going to use up the entire lecture time, so so people really need to remember to show up on time, because otherwise the end time is still going to be the same. Okay, I will not give anyone any extra time because people show up too late. So there we go. All right. So thank you for letting me know that the 21st is a holiday. It's kind of interesting how I really don't track, holidays. Usually it's my students who would remind me, but that day is a holiday. Okay, right. That's right. Practice exam is scheduled to be on the 14th, which is next Monday. There's nothing you really need to do. The scope of the exam is going to cover everything up to and including functions, but it would also include the material that we talk about today. So we'll see how far we can kind of talk about that today. So we'll see. Okay, so we'll see by the end of today, what the scope is going to be. But the practice exam, has everything up to and including what we'll be talking about today. All right, so 4-day weekend. That's right. Well, we have always had 4-day weekends, right? So that will make that it'll be a whole week before the class meets again. From the Wednesday next week to exam 1 is no, actually from next, yes, yeah, it's going to be a whole week. That's lots of time. Yes, so we are going to take the exam during class, and I promise no blue books will be required. So some of you already know the way I conduct my exams. The way it's going to be done, I'll just kind of give you a preview right now. I cannot really show you per se, but I can tell you what's going to happen. So about a few minutes before the exam time, which in this case is noontime, I will share a Google document with you, okay, and only you. So that document is very specific to each individual, to a individual student in class. That Google Doc is going to have the questions, and you just have to type your answers within the Google Doc. So one thing that is really important is not to type something outside of Google Doc and then copy and paste into Google Doc. So I want everybody to be typing their answers, just kind of incrementally into the Google Doc. Nope, no multiple choice. Yep, it's going to be all open-ended type of questions. So no multiple choice. Okay, yeah. So I was reading Chris' comment. All right. So I will keep an eye. Oh, there we go. Last discrete math class I took had multiple choice, and it was kind of awful. Well, it depends. It depends. We'll see. From the practice exam next Monday, we'll you guys will start to see the format of at least the exam from last semester. There's no promise of any correlation between the formats, between semesters. So usually I come up with some new type of questions or new way of asking questions every semester. No. The lowest exam grade score does not get dropped. If I had done that, if I had decided to do it, it would have been in the syllabus already. Nope, the syllabus says 20%, 20%, and 40% for the first, second, and the final exam. So there's no dropping of any lowest score of any kind. Oh, how do they ask proof questions in multiple choice? Oh, okay, I see. So you have to basically be able to read proofs really, really fast. Hmm. Well, multiple choice questions are also very prone to being defeated by people posting answers on Chegg and other websites. So I would never do something like that. Um, yeah, I think my exams are by design. I hope you're a little bit resistant to cheating. How can we write? Oh, that's easy. Okay, that's okay. Let me first address that question. How do we write, elements of and stuff like that? Well, that's assuming I require that, right? But even if I require that, it's like super duper easy. It's really point and click. Okay, so I'm just going to create this document here to kind of show people how to do that. All right, so let's just say that we got some really nasty piece of LaTeX thing that we have to write. Let me pick one from my own module. Okay, so Aleph Null probably has some really nasty ones right here. I'm just looking for one that is like particularly nasty. Oh, keep going, keep going, keep going. All right, so let's try this one over here. Oh, this one is even worse. Okay, so you do something like this: show math as tag commands, copy to clipboard, and then go to the Google Doc, and then go to insert equations. Where is that? Right here. And then, okay, I'm gonna wait until it's done. All right, so once you're here, there's a mode where you can just type it in. So I'm just gonna do a Control V, like that. Press the Enter key. Nope, that did not work. That didn't work as expected. All right, fine. Let's try something else. There's a way you can actually just type using LaTeX. I just have to remember how to do that. All right, so let's see. What does that do? Show document online. Equations. Okay, there has to be a mode where you can just type in. Okay, so maybe it's just that. So, oh, okay, what just happened? I closed the document. All right, fine. Let's make another new one. So the bottom line is, if that is actually needed, it can be done. You just have to use the equation editor here. Okay, so let me try it one more time. X in the set of A, B, C. Yeah, so you can use a mixture, so I think copy and paste is not going to work, but as you saw what I did, it's when I X, automatically is converted, and then you do a backslash and then in, that gives you the element of, symbol, and then the braces do not need to be escaped anymore because, it's not strictly LaTeX, so it's just, the curly braces, 1, 2, 3. If you want to use a there exist, okay, then you just do a backslash. Oh, okay, you have to get into the equation first, and then the backslash exists, and then the space, that converts it into the existential quantifier. Yeah, so there's that. Yep, there we go. Oh yeah, the exam is open notes. Open book and open notes doesn't make any sense not to, right? Because the notes and the modules only contain knowledge. I really do not want you guys to waste your brain capacity just to memorize stuff. So now the question is, if I don't want you guys to memorize anything, what am I going to test? What would be the nature of the test? What am I going to be testing? This is actually testing to see whether you guys have read the syllabus, because it was actually talked about in the syllabus itself what kind of assessment I will give you as a class. Alright, so let's go back to the beginning and we'll take a look from here. That's okay. Okay, so to answer my own question, I'll be testing whether you guys can apply what you have learned. That's what I'll be testing. In other words, depending on who you're asking, some people would say that every single question from my test looks like a brain teaser. I don't think that's the case, but that's what some people say. Anyway, so we are continuing with today's topic, and we talked about this already, which is can we find a function f that maps from the set of all integers to the set of all natural numbers? And this is one way to do it. Okay, there may be other ways to do it. All I need is to find at least one function that has the set of all integers as the domain, the set of all natural numbers as the codomain, and the function has to be bijective. Yep, exactly. So Philip is right. Okay, it's all about critical thinking and problem solving. Cool. So now let's look at this ternary expression. And if you cannot remember ternary expression, like what is this question mark doing and what is this colon doing here, you need to go back and look up ternary expressions or ternary operator of C++. It is actually quite useful. Well, it's not exactly absolute value, because absolute value is not bijective. It would map 1 and -1 both to just 1. But I need something that's bijective. So this one is actually bijective. So the way we test this is really just to plug in a specific value. Let's try 0 first, right? So let's just say that x is 0. X is 0, so 0 is greater than or equal to 0 is true. Then we use the middle expression as the return value. So 2 times 0 is just 0. So f of 0 is 0. Alright, so let's try something else, right? Let's try f of 1. 1 is greater than or equal to 0? Yes. So 2 times 1 is 2. So what this does is it will map all the positive, or I should say non-negative, okay, all the non-negative integers to 2 times that non-negative integer onto the natural number set. Okay, so that's fairly easy. Okay, so if you give me 1, I'll give you 2. If you give me 16, I'll give you 32, and so on. The negative ones will map to odd numbers. So if you say, let's just say x is negative 2. Okay, so if x is negative 2, -2 is greater than or equal to 0 is false. Then we jump to here. So we multiply -2 by 2, which is -4, but then we negate it, which means we only get 4. 4 minus 1 is 3. So f of negative, what was it again? 2. -2. So f of -2 will give you 3. So it's basically just, let me see, my camera is on. So I'm trying to kind of motion this. So let's just say that these are negative numbers and these are positive numbers. So the way it does it is to space out the non-negative numbers first, and then it will kind of map it like this. Is that okay? Does everybody see what I mean by this? I hope this is not a gangster sign. I don't think it is, because it's a little bit complicated, to be a gangster kind of sign, but just want to make sure. Yeah, we certainly do not want people to say that, but tech is doing gangster signs in class. It's like, Okay. All right. All right. So one thing you can do, okay, is to get good at spreadsheets, because using a spreadsheet, you can just kind of enter the equation, that represents exactly the same type of formula, and then you can just visualize, how things are going to work out. I will give you an example here. Okay, so I'm going to use a different sheet right here. All right, so I'm just going to give you a very small example. So I'm going to start with -4, and then this cell here is 1 plus whatever the cell above it has. So this way I can just kind of do something like this, and it just gives me a very short series of numbers. And then on this side, I'm going to implement the function that I talked about on the other side. So there are a few ways to do this too. The way I'm going to do this is really just to make use of spreadsheet formulae, and not to use any not to use any Google script functions. You can do it in Google script functions too. I mean, that's another way to do it if you do not want to kind of deal with spreadsheet functions. So it's going to be if, and we want to see if this particular value is greater than or equal to 0. If it is, we want to return 2 times whatever this cell has. Otherwise, we return -2 times whatever this thing has, and then we subtract 1 from it, from the product, and there we go. So now we have these values on the other side. So this kind of helps because because I can talk about how the non-negative integers just kind of map to even numbers in the natural numbers, and then all the negative integers map to odd numbers. But this gives you a kind of more visual way to kind of understand what we are talking about. Alrighty. So I hope. Are there any questions about how I used this spreadsheet to kind of visualize the mapping from integers to natural numbers? Oh yeah, yeah. This is not CISP440. I made an assembler out of Google Sheet. Yeah, so Google Sheets are more flexible than most people give it credit for. It's not as good as Excel when it comes to formatting, but when it comes down to text processing, oh, the kind of regular expression you can use in a Google Sheet formula is great. All I can say is it's great. It just works really well. All right, so there's that. So the next question is to ask, well, okay, this is a function, okay, given any integer, it maps to one and only one natural number. But are we guaranteeing that it's mapping to a unique natural number? Right? Is this bijective? And also, in addition to being injective, we also want it to be surjective, which means for every natural number, I want to find out, who or what integer maps to it. So there are 2 ways to do this. Yes, it's not an if statement, it's called an if formula. All right, so here's the question, okay? Yeah, because I want you guys to learn how to think and how to learn by yourselves, right? So what do you do when you saw what I just did and you go like, whoa, what did you just do? Okay, in here. Okay, so you can see how I use if. Okay, so what do you do next? You go search, right? So you go to a search engine and then you just look for it. You cannot see how I search, so I'm gonna have to go to google.com first. Then you can see how I did the search over here. All right, so now we can search for if Google Sheet if. There we go. And we'll just go for that. If function. So now we get to the help, in Google Sheets, and that's it, right? So that's how we try to become independent self-learners. It's like That looks kind of interesting. How did that work? Okay, so the moment you know the name of whatever that thing is, you search and find out, by yourselves, how that works. Yep. All right. So just little tips of, what you can do, when you see something that is kind of new, and it's like, okay, that looks kind of interesting. I want to know how that works. All right, my watch just buzzed me. It's time to take roll. And today's word for roll taking, I'm just going to put it into the text channel. There are two of them. You can use uppercase M. You can also use just lowercase m. So both of those words will work for today's roll taking activity. And today is the 9th. So I have just shown the roll taking activity for today. If you refresh your browser, you should be able to see it. And then the words, choose one. Okay, once again, choose one of the words, either uppercase or lowercase m macros. Yep, I watched the original Macross, and I think that was 1980 something, 1982, 81 ish. And there's a reason why I chose Macross as a roll taking word for today's class. So we'll go ahead and find out why that is the case. Yep, that and Gundam basically redefined the mecha genre, for Japanese anime. I think Gundam came first, and then Macross was second. But they both redefined Japanese mecha anime. Well, they are our brethren, right? They're actually related to us. The Zenratis and the female race of the same thing. Basically, they're version 1 and we are version 2. That's the that's one way to see it, right? For those of you who know what I'm talking about. Oh, no, I just kind of hopped on to talk about the Japanese anime Macross. Nope, there's only one. There's only one road taking quiz of today's date on it. Today is February 9th, so just do that one. All right. All right, so assuming that is okay, then we're going to work on the inverse of this, okay? And then we're going to move on, okay? So we'll work on the inverse. So if I just use the spreadsheet, okay? So now that I have a spreadsheet, let's just use the spreadsheet for that. So if I have only column B and I want to reverse it back to the integers, how am I going to do it, right? So the first thing I'm going to do is to hide column A so that we don't see it. So now we can actually concentrate and go like, okay, so what do we do if we are only given a natural number and I want to reverse that process? Okay, I want to find out which integer is mapping to the natural number in column B. So the first thing that I need to do is to see whether it is even or not, right? So I'm going to have to say the mod of this value and 2, okay, and I want to see if it is a 0 or not. If it is a 0, then I know it's an even number. If it is a even number, then it's going to be just this value divided by 2, because that's what we did in order to end up with 02468. On the other hand, if it is an odd number, then we have to reverse the entire operation, which is to add 1 first, okay? So now we have to get back to this value. Okay, I need parentheses now. So I need to get back here, look at this value, add 1 to it, and then we have to divide it by -2. There we go. And let's see if that works. So, and I'm going to just do this and see whether we got everything back. And we did. So this is an inverse function right there. And we got some. Oh, okay. So there's a bunch of row taking activity. Yeah, the other one I cannot get rid of. So just look for today's date. Yeah, just look for today's date when you try to get to the row taking activity. Yep. Yep, and the other one is from 2021. I probably should be more careful to go over all of those and just kind of get rid of, or at least hide the ones that do not apply. All right, so now we have a bijective function because I just gave you one way mapping from integers to natural numbers, and I gave you the inverse, which is mapping from natural numbers back to the integers. So now that we have a bijective function, what is the significance? What is the whole thing here? Why do we want to do something like this? Because we want to say that the cardinality of the set of all integers is Aleph null. In other words, we have just established this equality here. The cardinality of integers is the same as the cardinality of natural numbers. They are both what we call infinitely countable as a set. All right, so that one seems to be easy. Okay, this is basically just the same thing that I entered into the spreadsheet, except it is in a using a ternary expression, checking whether it is even or odd. If it is even, it's just x divided by 2. Otherwise, it's x plus 1, the whole thing divided by -2. So it's exactly the same as what I have in the spreadsheet, just in a different format. So these are called infinitely countable sets. This one is pretty easy. So the next thing I want to do is to see if something a little bit more challenging can be seen that way or not. All right, so this is why I have a spreadsheet here. So the thing is, the coordinate of this thing here. So let me just first present the coordinates. So I'm gonna call this one at coordinate 0, 0, and then this one here is at coordinate 1, 0, and this one here is at coordinate 2, 0, and so on. Okay, so basically, this whole thing is row 0, and then this whole thing is row 1. So I'm not referring to the spreadsheet designation of the row. This is just kind of focus on the content area and not to look at the column name nor the row name in the spreadsheet. So this would be column 0 and row 1, and this would be 1, 1. This would be 2, 1, and then this one here is going to be 0, 2, 1, 2, and so on. So are we doing okay so far, in terms of knowing how to name the coordinates of a particular cell in this table? So I just want to get a confirmation about that first. Okay. All right. Cool. So if you look at it this way, you can kind of see this as a Cartesian product, right? This looks like a tuple, doesn't it? It is surrounded by parentheses, and there are 2 items in it. So it's a 2 tuple. Okay. This is also 2 tuple, and everything here should be 2 tuples. Yes, so it's kind of the xy coordinate system. So the first number is the x coordinate, and then the second number is the y coordinate. So, all right. So now what we have is something that looks like this. Let me go back to the notes that I just typed today. So now I'm looking at a domain of natural number Cartesian product with natural number. In other words, the first part here, the domain, is what we are seeing, what we are visualizing here. The question is, can we map the Cartesian product of natural number and natural number to just natural number? That is the question. So I am not folding, I'm not folding one side of the line, onto the other side of the line this time, I'm actually having a two-dimensional thing, and I'm asking, is there a way to map it to a one-dimensional thing? I'm dropping a dimension. That is the question. And the answer is yes, okay? And it turns out to be actually pretty easy to do, okay? So let me just kind of go back here, and let's see. I'm trying to find out, how I can give you a general way to describe a cell. So let's go ahead and work out the not Excel, the Google Sheet formula to do this. So to do this, we're going to have to use concatenate or just concat. And I'm going to searching on the side because there are two. Hopefully there's one that is easy to use. I know how to do one, but I want to know how to do the other one, which allows me to concatenate more than just two components, because the one that only concatenate two components is not handy. This one doesn't. This will work. So concatenate. Okay, I misspelled it. Concatenate. There we go. Alright, so when we have concatenate, it's really just a concatenate thing. So we'll start with open paren, okay? And then the second thing is going to be, let's see, the column number. So the column number is really just column minus 1. And column, is a function that returns the column number of the cell that contains this formula. And then we have a comma as a string, and then followed by row number minus 1. The reason why I have a minus 1 is because the designation of column number and also row number are 1 oriented instead of 0 oriented. So I have to kind of offset everything by 1. And then the last one is the close parenthesis. Yep, that works out. Cool. So now I can do something like this, and then do something like this. So it's really just an idea of how do we assign a two-tuple name to each cell. And you can see that this is like, oh yeah, this is not very exciting. This is exactly how we designate a pixel on the screen, right? Okay, not a big deal. So now the question is, when we look at something like this, okay, is there a way to assign a natural number to each cell in a unique way? In other words, we want a bijective function so that we can assign natural numbers to the cells. So how would we do something like that? Well, I'm hoping that some of you, at least some of you, have read the module, because in the module, I first described this method as, okay, so let's do something like this. Okay, so I'm going to do it by hand first. So I'm going to assign the numbers like this. This is going to be 0. And unfortunately in the notes, it's going to be, the picture is going to be upside down. So this is going to be 1, this is going to be 2, 3, 4, and then 5. And then we have 6, 7, 8, 9. And I'm pretty sure you guys can now see the general pattern, right? This is 10, 11, 12, 13, 14, and so on. In other words, I'm basically just scanning, with diagonal lines, starting with the origin. Then this is the first diagonal line. This is the second diagonal line, the third diagonal line, and so on. Okay, so I'm going to do something here that to kind of make this easier to read, because when the cells are too wide, it doesn't look like pixels anymore. So if I just kind of shrink the cell size a little bit, it looks more diagonal like this. So at this point, I can start to insert some kind of notation, and we can say, I think there's a way to insert picture elements into it, or maybe not. Nope. I was trying to kind of add arrows to the whole thing. See, that's not what I want. That's probably not what I want. Okay, so maybe not in Google Sheet, but I'll be okay. I mean, I'll be seeing how I just kind of scanned, like starting with this. This is one diagonal line. This is one diagonal line. This is one diagonal line, and this is one diagonal line. So including 0 as a kind of deformed diagonal line, we have 5 at this point. Are we doing okay so far with that method? I'm just checking to make sure my Discord is not disconnected. It is still connected, so I guess people are just kind of thinking about it. Oh, crickets! Yes, yes, I need to do this. There we go. All right. So are we understanding, how I assign a natural number to each cell? Okay. Um, so the task that I want to do is to look at this, okay, where I originally start with a two-dimensional xy coordinate to designate one cell, right? So with this cell here, it is 4, 8. So in the second method, I'm trying to assign natural numbers to each cell in a way that is bijective. So if you give me the two-dimensional coordinate, okay, I should be able to give you the natural number corresponding to that cell. So for instance, if you give me 4, 9, then I should be able to tell you what 4, 9 should have as a natural number on that cell. Well, yeah. So we want to be able to count all the cells, but we want to do it in a way where it is bijective. We don't want two cells to have the same value. And I'm going to do something here, hopefully to help out a little bit, because I think this will help kind of visualize what we are talking about. So this is one diagonal line, and I'm just going to alternate, between the diagonal lines. So this way, you guys can just kind of look at this and go like, yeah, I can start to see some diagonal lines. There we go. All right. And then Ian says, so using this bijective method, we are transforming two-dimensional coordinate into one-dimensional natural number. Yes. And then Chris said, you can't just go across or down because you will never get to the end of the row or column. And then Philip said, to add arrows in sheet, it would be under the drawing tab. All right, so let's see. Drawing tab. Okay. Not sure exactly what. Okay, show, insert, then drawing. Okay, so insert, then drawing. Yeah, that's not going to help because it's really just inserting a drawing on the in the spreadsheet. It's not going to be related to one of these items. I think this is one of the things where Google Sheet does not do as well as something like LibreOffice or Excel. Yeah, I don't think there's an easy way to do this. I can make the text slanted. I mean, but that's not what I want. I want to actually, literally, I want to draw an arrow, down here. Yeah, I don't think we can easily do that, but that's okay. You mean, are we still okay here? I mean, are you guys still okay, or do we have any further questions? All right. Let me illustrate this in a slightly different way. Okay, so I'm just going to go back to the previous sheet and say, okay, I'm interested in 4, 9, which we know as E10. Okay, so I want to go to E10 in the spreadsheet. Go to sheet 3, and then go to E10. So this is E, and 10 is down here. So I want to know, if I just kind of start to fill up, each diagonal line with natural numbers like this, what is going to be the natural number over here? That is the question, okay? So most textbooks, okay, that talk about this topic will not give you the closed form equation. It will just say, oh, let's just fill in all of these values and just keep going diagonally until you get to this particular cell. Then you will know what value it is supposed to have. That's what most textbooks will talk about this, and then they just move on to the next topic. Well, that's not good enough for me because I want to have a closed form equation to find out what this value is going to be. So in the notes, I actually went through the rationale, basically how I derived the closed form equation. Okay, it is actually quite useful if you want to know how to solve a problem. This actually is me trying to show you step by step what went through my mind in order to come up with the closed form equation, which is this thing here. Okay, so g of xy is taking a two-dimensional coordinate and it's returning a natural number, which is what the value that is supposed to go to that cell. The derivation, oh, okay, so I can just kind of quickly explain it. Because sometimes if I explain it interactively, it'll be easier. So if you look at the first diagonal line and you ask what is going to go here, well, the first diagonal line only takes up one cell, so whatever the value is for this is the base of the first diagonal line. So at the base of the second diagonal line is going to be whatever this is plus 1. But then the second diagonal line has two cells. So the starting number of the third diagonal line is going to be whatever this one is plus 2. And then the third diagonal line has 3 cells. So whatever the start number is for the third diagonal line, if you add 3 to it, it becomes the beginning of the fourth diagonal line. And then whatever this is, you add 4, it becomes the starting point of the fifth diagonal line, and so on. So if you just look at this pattern, okay, just ignore the rest of the table for now. If you just look at these 5 numbers, and I'm going to ask you, what do you think this next one is going to be? What do you think it is? Not even knowing that we are trying to solve this specific problem. If I just give you a pattern, okay, if I give you a portion of a pattern, what do you think this is going to be? 15, exactly. By the way, this is the kind of question that IQ tests will give you, is they give you something and they want you to recognize what pattern are we looking at. So this is going to be 15, and what about this one? It's 21, and this one is going to be 21. Let's see, this is plus 5, plus 6, this is plus 7. Yep, 28. Yep, you guys got the idea, okay? So the first thing we want to do is to say, that seems pretty tedious, right? So in order to get to this point here, I'm going to have to ask myself, what is 0 plus 1 plus 2 plus 3 plus 4 plus 5 plus 6 plus 7? Is there a better way to do this? Is there a closed form for the summation? So without replicating my own notes already, that's already here, I'm just going to say, okay, at the base of all the diagonal line, that's why there's a 0 here, because the y coordinate is a 0 for all of those. So if I'm only interested in column x, okay, because remember x is counting horizontally. So if I want to know what number goes to the cell that is designated as x0, I'm really just adding from 0 to x, right? 0 plus 1 plus 2 plus 3 all the way up to x. So that one is a little bit interesting because I break it up into 2 parts, okay? Because you have the case when x is an even number and x being an odd number. So I break it up into 2 parts. Don't worry, I'm not going to bore you with the details here. But eventually we end up with something that looks really nice, okay? So x times x plus 1, the whole thing divided by 2, is the closed form value of something that looks like this. All right. So that's helpful, okay? Because using that particular method, now we have a way to fill in the values for the base of all of the diagonal lines. Okay, so let's just plug it in and see if that works. Okay, so instead of a 0, which is a literal constant here, I'm just going to try that out, right? So we want to use equal, and x is really column -1, column -1, and we want to multiply that to column -1 and then +1 this time. I mean, obviously that kind of cancels out, but I'm just going to type it like this: the whole thing divided by 2. Oh, okay, I must have made a mistake. It's times, not plus. Oh, what did I do? Because I did not spell out multiplication. The shorthand doesn't work. Alright, so now if I just kind of extend it, let me just extend it to cell D1 just to make sure that we still got the same value, so you can see how it is actually working out for the base of all the diagonal lines. Alright, so Luke said, so it's okay if I don't understand where you got the upper and lower limits along with the terms from. Well, the derivation is already here, so obviously I'm not going to ask any questions about the derivation itself. But the rationale of how I derived the closed form is something that can be helpful if you want to learn how to problem solve something and how to recognize patterns, and from the recognized patterns turn something into an equation, into a formula, and so you have a closed form equation to solve something. Then following the steps can be helpful. It's very tedious, okay? There's a lot of tedium involved in this derivation, but I think the process is something that can be helpful. You mean the next step? Oh. I'm not really sure what you mean by the next step. Okay, so from here to here, I'm just gonna add let's see, 13 to 78. That becomes the value of this cell, and so on. So 78 plus 13 is 91. So let's see if the next one is 91. Come on, come on, crap. There we go. It is 91, and so on. Yeah, it's already. Oh, this is the nice part about all this. Okay, this is already shared. If you go to the class website and go all the way to the top, there's a link to shared folder. It's already in the shared folder. The name of the spreadsheet is space folder. That's the name of the spreadsheet. Oh yeah, you guys can actually follow the changes. Opening this on your side and be able to follow all the changes, so you get to see all the equations and whatnot. Yep. All right, so now that we know how to find out what the base, or the natural number corresponding to the base of all the diagonal lines, so now the question is, what about the other cells along a diagonal line, like this one over here? Let me see, maybe not this one, maybe this one over here. So how do we know, the value corresponding to the cell? So the trick is to track it down to the base, right? So you say, okay, this is the one that I'm interested in. Let me just use question marks to mark what I'm interested in. So now we say, okay, which diagonal line do you belong to? Okay, it belongs to click, 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 click. Okay, not quite, but it belongs to this diagonal line. Okay, so this is the diagonal line. I have to extend this 2 more cells to find out the value of the base of that diagonal line, which is 120. So that makes this 121, 122, 123, 124, 125, and this is 126. Oh, okay. So Luke just typed something in the text channel. I'll talk about that when we have time, okay? Because today is I'm a little bit crunched for time because I want to cover the high level concepts so that on Monday we'll have everything that we need in order to participate in the practice exam. So the derivation, I will actually go back and talk about it on next Wednesday. but I want to talk about how the function works, just in general. All right. So the y coordinate, which is 6 in this case, is actually going to tell me, okay, once I find the base of the diagonal line, just add the value of y to get to the value of this particular cell. So the closed form for each cell, okay, I'm just gonna is this thing here, but we also have to add the row number to it. So I'm just gonna put this here. It's going to be the row number minus 1, because once again the row number by itself is 1 oriented. We want it to be 0 oriented. So now that I have this, I am just going to use the copy method to go over, and this one I said what, 127 or 126, I cannot remember. No, that is not working. Okay, let me see. Oh, right. Okay, I forgot one thing, because I have to add the column number and the row number together. Okay, so I forgot about that, because we have to find which diagonal line. So we have to add the row number minus 1, and same thing over here. Because it's the x plus y, like so. There we go. Alright, so I think this is what it takes. Alright, so let's get back to here. Yes, that works. Alright, so we got a few questions in the text channel. So Ian said 126. Excellent. And this is another way to get the same answer. Yep, that's right. All right, so I now have a closed form equation, okay, to basically say, oh, I don't need to fill in the diagonal lines all the time anymore, because now I have a closed form formula. If you click on one, that's how I do the calculation. Now, I know this looks, kind of ugly, because row minus 1 is basically what y is. Column minus 1 is basically what x is. So when you go back to the notes, the closed form is fully derived down here. It's x plus 1 times x plus y times x plus y plus 1, the whole thing divided by 2 plus y. And that corresponds to the formula for each cell in the spreadsheet. So the spreadsheet is basically a visualization, using the function that is already derived in the notes. But this is basically a quick and easy way for you guys to see, oh, so if I just pick a particular cell, how do I calculate the value of that cell? It's just this, okay? You just use the x value, the y value, x plus y, the whole thing, times x plus y plus 1, the whole thing, divided by 2, plus y on the outside of the quotient. And that's it. So the notes actually go through, basically small, tiny little steps to resolve to the final form like this. So now the question, a separate question, is to go back to something like this. And now, oh, okay, I see one of you is already here. Nice. Anonymous Moose is already here. So this is a great way to utilize the resources, because you can actually click and look at things when I'm talking here. So that's actually helpful. Anonymous. Okay. All right. So now the question is, if I give you a natural number, let's say 1001, okay? How do I figure out which cell has the value of 1001? Now you can say, oh, we just have to fill this table until we see 1001. Well, that's one way to do it. But if I give you some gigantic number like 20,613,000, how are you going to do that? I mean, that's just not, it's just not a good idea to say, oh, we just have to fill in this table until that number shows up, right? Because your spreadsheet may run out of space if I choose a really gigantic value. So that goes to the second part of this module, which is a whole lot more math, but nothing that you guys cannot deal with. Okay, so the reverse function, the inverse function, or the way I try to work out the inverse function starts from here. Our new challenge is to find x and y for a given natural number. In other words, I'm trying to find g inversed in this case. So there's a little bit of observation, there's a little bit of inequality, solve for the inequality. This is quadratic equation, you guys know this already. But of the two roots, I'm only interested in one because I know that the solution that I'm looking for cannot be a negative value because we want to go back to a natural number, two natural numbers. So there should be nothing negative of the value. So I can concentrate on only one of the roots, and the root that I'm concentrating on is W, and then from there, I just kind of work the math through a little bit. So by the time we finish with this, fast forwarding a whole lot, I define a function called Wn. So if you give me a natural number like 1001, I apply W of n, I end up with a specific natural number. Okay, this is the floor symbol, by the way. This is the floor symbol, which is returning it. You can look at this as truncation also. Okay, we're just getting rid of the fractional part because as long as whatever is inside is non-negative, it works the same way as truncation. Oh, the floor function? Yes. So the floor function returns the largest integer that is less than or equal to whatever you're taking the floor of. Alright, so I know it doesn't it's hard to just listen to it. I'm not an audible learner, by the way. So if someone is just to tell me something verbally, I think by the time that person is in the middle of a sentence, I would have forgotten the first part of the sentence. So that's how bad I am when I'm listening to something. So it's better to just to define here. So I'm going to use the symbol so that you guys do not get bored to tears. You get to see how I'm typing this. So the L floor is the left hand side of the floor symbol, and then I have an X, and then the right hand side of the floor. Alright, there we go. Is the largest integer that is less than or equal to x. There we go. Yes, I know I'm mixing up, mathematical symbols and English sentences here, but it kind of conveys, what it is. Okay, you just give me a value of x. X can be any rational number. The floor of x is the largest integer that is less than or equal to x, and that's it. That's the definition of floor. And Chris had taken CISP440, so I'm picking on Chris here. That symbol was actually introduced in CISP440 as well. So, but that's not important. So the important part is I define a W function. So the W function is really just to solve for a part of the root, and then I apply Wn in this way. So now if you give me a natural number and you want me to find out what is the x and y coordinate corresponding to that natural number, this is the x coordinate. Okay, this whole thing here is the x coordinate, and this whole thing here is the y coordinate. The bottom line is there's a way to reverse it. Okay, the key point here is there's a way to reverse the g function. So now we have a function going forward, going from the two-dimensional coordinate system to a natural number, and we have a way to go back. Okay, give me any natural number and I will be able to show you which cell in the two-dimensional space is supposed to have that natural number. So now we have a bijective function again. So once we have a bijective function between the Cartesian product of natural number and the natural number itself. Okay, let me go back to the notation earlier, just so that we can it's easier to see it that way, what we are dealing with here, by going back to the g of x the first time we talk about it. Where is it? Maybe I didn't talk about it here, but I definitely typed it over here. There we go. Okay, so we are talking about this g over here. So we found g. Okay, there's a way to define the g so that it is bijective. That's the bottom line. Okay, g exists, and there's at least one g like this, and it is bijective. So the significance of that is we can now claim that the cardinality of this Cartesian product is really the same as the cardinality of just the natural number itself. Let me say that one more time. The cardinality of the Cartesian product of natural number with itself is exactly the same as the cardinality of just the set of natural numbers. Okay, I'm not. So why is this important? Okay, this is tricky because it's playing a mind trick on you. Okay, because most people say, oh, the cardinality has got to be bigger when you have a Cartesian product of a set with itself. It should not have, it doesn't make sense that it has the same cardinality as one of the components of the Cartesian product. But it does. Okay, it does because we have found this function g that is bijective. It maps between the two-dimensional coordinate system and the set of natural numbers in a bidirectional way. It's not double. You cannot double infinity. the double of it doesn't make sense, right? Because yes, so Luke is right. Okay, it's the degree of countability. Okay, and that's why there's a aleph null or aleph zero here. So whenever you see something that looks like this, aleph zero with a subscript zero, the natural tendency, at least in my case, is to say, so what is aleph 1? What is aleph 2? Why do we have a subscript here? Because if aleph 0 or aleph null is the only thing that we need to understand, the only thing that exists, there's no need for the subscript of 0. So the fact that it has a subscript of 0 suggests, right? There's going to be an aleph 1, aleph 2, and so on and so forth. So these are different classifications of countability or equivalence of cardinality. So aleph null is all about the cardinality of the set of all natural numbers. Sort of, in a way. We will get to the quote-unquote big O notation. Now I said big O with quotes in my hand gesture. Once again, I hope this is not gangster gesture. Hope not. It's because it's not really big O. Okay, and we now know that Greek letter very well. That's actually big omicron. I'm not kidding you. I'm not kidding you. It is actually what we see as big O, in time complexity, notations, is really big omicron. And we also abuse, okay, we use it incorrectly too, and I will say that most programming professors would actually make that mistake. Is what we really care about is not the big O notation. What we really care about is the big theta notation. So we'll get to all that stuff, later on in this semester. Okay, so we have big theta, big omicron, and big, I think it's big phi. Yep, and they basically correspond to the upper bound, lower bound, and the tight bound of the estimate of how long it takes for an algorithm to finish. So we'll get to that, kind of close to the end of the semester. So to answer Chris's question, it's sort of like that, but not really the same, because this has to do with equivalency of cardinality of sets that have a infinite number of elements. Because if you look at this, okay, just the set of natural numbers has an infinite number of elements. And needless to say, the Cartesian product between the set of natural numbers with itself is also going to have an infinite number of elements. So, but the key concept that we have just illustrated here, which also relates to why I chose macross as a name, is you can actually fold a two-dimensional space into a one-dimensional space. It's dimension folding, right? And that's what macross does. Okay, macross is SDF1, which stands for super dimensional fortress 1. Okay, it travels by folding space, and this is our mechanism of folding space. So I know we are running out of time, but this is also important, because if you can fold two-dimensional space into one, then you can nest the folding. So if you start with, let's say, five-dimensional space, okay, you can fold two of those dimensions into one, then you only have four dimensions left, right? You choose any two of those four dimensions, you fold it into one single dimension. Now you have only three dimensions left. And then you fold any two of the three into one, then you have only two dimensions left. And then finally, you fold those two into one, and it becomes a line. So you can start with any finite number of dimensions and eventually fold it into one. Now, obviously, we're only dealing with natural numbers or integers in this case, so we're not dealing with real number dimensions. But it is still kind of interesting, right? Because you would not, I did not expect the Cartesian product like this to have the same cardinality as the component of the Cartesian product, but it does. So that's kind of the significance of this entire lecture. Not so much the details of how things are derived, but the fact that you can fold dimensional, any number of dimensional space, as long as each dimension is made out of just natural numbers, we can keep folding until it becomes a line. Yes, well, okay, that's very funny, Danny, because origami also involves, guess what? Folding. So it's interesting how you chose that analogy. I'm pretty sure that's intentional. Mod 3 instead of mod 2. Can you fold 3D directly into 1D? You can probably do that. Okay, so I understand what Luke is asking. So for the rest of you, if you think you're done with today's lecture, it's done. But I want to kind of talk about, in Luke's question. So the way you do this is you extend the approach of filling in quote-unquote diagonal lines, right? So when you start with a two-dimensional space, you have a diagonal line, and by scanning the diagonal line, orthogonal way, in that direction, you can fill it up the space. So when you have a three-dimensional space, then you look at not a dimensional line, a diagonal line, you look at a diagonal plane. So if you think about a cube, okay, look at a corner of a cube, and then you can draw a triangle, an isosceles triangle, and say that is my diagonal thing. Okay, the diagonal thing is just one dimension less than your starting space. So now you have a isosceles triangle, and then within the isosceles triangle, then you can scan within the isosceles triangle in a specific way. So the idea is, yes, you can, instead of using a nested application of the G function, you can actually go directly from 3D space to 1D space by looking at the isosceles triangle, which is now your diagonal plane, and then within the plane you have your scanning method to go through the lines. So it's just a way of looking at space like that. It's not exactly, I suppose you can do it in a spiral way, because the isosceles triangle has its fixed size, right? So it's fixed size, so you can always kind of like you can fill it in a spiral way, or you can just fill it in using a scanning way. So how you fill in that triangle is up to you, because it's a finite space to begin with. So whatever you want to do within that space is up to you. But the idea is you move that diagonal plane kind of orthogonal. So the direction of how you move the diagonal plane is orthogonal to the plane itself. Then you gradually fill up the three-dimensional space that way. All right. No, that exclamation point is not factorial. It just means exclamation. It just means, whoa, this is fun. This is interesting. How can they be the same? Alrighty, so I'm pretty much done. The concept of dimensions is very useful for linear algebra. Yes, just the other day I was reading on a linear algebra concept. They talk about, I cannot remember the name of that thing. As okay, never mind. Nope, it is aleph null exclamation point. It is not no exclamation point. Alrighty. Well, I think we are done for today. So over the weekend, if you have time, I think just kind of reading through, trying to dig through the notes. I know it is a little thick, so you can use a fork and a knife to do it. But try to dig through the rationale of how I derived the closed form equations, because that is illustrating how to problem solve, right? This doesn't involve any math beyond pre-calc. Okay, so if you have taken calculus classes already, you already know more math than you need in order to get this done. So it really is just algebra for the most part, and quadratic equation. This is as math as it gets. Okay, is quadratic equation. But the question is, how do you utilize all those tools, okay, up to quadratic equation to solve a problem like this? And if you want to learn how to problem solve, it might be useful to kind of read through the notes. All right. Cool. Alrighty. So I'll see you guys next week. Don't forget you have an assignment due next Wednesday. Yep, go ahead. It's basically a bitmap kind of type of answer. So let me kind of give you guys a preview. So you basically just add up the numbers that are applicable. The sum is the answer. Does that help? All right, so I can give you an example. Oh, that's not what I want. I'm not grading it because you guys haven't turned in anything yet. Excuse me. All right. I want to do a preview. So there you go, preview. All right, so every question has kind of the same format. So if you think something is a function, add 1 to the number. So you start with 0, okay? You start with 0. If you think the function is, whatever f is indeed a function, using x as a domain and y as a codomain, and it is a function, then you say, okay, add 1 to the sum. If f is a function and it is also injective, add 2. So now you have 3. And if f is a function and is also surjective, then you add 4 as well. So your answer would be 7 for a bijective function. Does it help? Well, you just add it up, right? Whatever the sum turns out to be is the sum. Now, some of those numbers do not make sense, but I'm not going to tell you which number does not make sense, because that's actually testing whether you understand the concepts or not. I cannot answer that question. Okay, all I can say is yeah. Yes, 1, 2, 4 are the components. Yes, you can have. Okay, I'll put it this way. You can have 1 or 0 of 1. You can have 1 or 0 of 2. You can have 1 or 0 of 4. So that makes so your number is going to range from 0 to 7. I'll put it that way. So your answer, whatever you put here, should be an integer or a natural number from 0 to 7. So you have 8 choices for each question. All right. Alrighty. Alright, so I'm going to stop the screen share. I'll still be watching and looking at the text channel until it quiets down. So I'm going to stop the screen share and also the streaming.